And let's see, where am I looking for? Where's my keynote? There we go. So kind of recapping stuff that we've talked about. And we're going to look a little bit more at graphs. So today, I want to start kind of putting together all of our pieces, make sure we're good going into the weekend. You're going to be studying this weekend. You got a test a week from today, but there's no class on Monday. Monday is Labor Day. So I'll see you on Wednesday. We'll finish any last minute sort of questions and kind of extending what we know to see how much you know about what you think you know. And then we'll take a test on Friday in class next week. But we've been talking about linear functions, and you haven't necessarily written entire functions a lot, but talking about this constant rate of change, which creates, visually speaking, functions that form a straight line of some sort or another. So just starting back from the beginning in the sorts of change we saw, we started talking about change in just a single quantity, like the number of gigabytes of memory taken up on your phone. And maybe we could have related that to how many programs you installed, but it's not going to be a nice function relationship. It'll be all over the place. Every program's different. But to calculate change, if you only have one varying quantity that you're considering, like not considering what changing one does to something else, but just changing one thing, we can think about just the simple, y final minus y initial gives you a change in y, or whatever the letter is. I'm just using y as an example. Or alternatively, and that's really just a rearrangement of this, if I need to find a new final value of y, take my starting point and append a bit of change, which it could be a negative change. So in reality, you might see something with a subtraction, but if I have a starting value and then I add or subtract an amount of change away from that starting value, I get my new value, final value, or later value, other value. But what we spent more time on is dealing with constant rates of change between two related quantities. So when we had that relationship, instead of just a single variable, we had a different way that we could compute this dy. I'll use y as the dependent variable here. We say dy is a constant multiple of dx. So if x and y are our two related quantities, if x changes by some amount, any amount, I know how I can calculate how much y changes by using this multiple, this constant rate that relates the two. So this is our definition of this constant rate of change we were talking about the last, on the quiz. We were talking about for any additional number of gallons of water, multiply by 8.3, 8.2, whatever it was, to get the change in the weight of the barrel of water. One quantity's change multiplied by a constant gives us the other quantity's change, regardless of the size of that change. Or alternatively, you could express what the rate is by, if you had the two corresponding changes, you could divide them to find that rate of change, if that's what you know. So visually speaking, we looked at some of the animations in the textbook, and if it was just a single quantity, I don't think we looked at this, visually, not animated here, just a stagnant picture, but if I have just one quantity, just graphing on one axis, if I start at some initial value and I change in one direction or the other, I can get a final value. So y initial to y final, the difference between those is the dy. The initial value of y and a final value of y are all relative to some starting point. In this graph, it seems to be they started at 0, y initial, like an initial y value. If I graph it, that's how far it is from 0. If I say y is 7, that means it's 7 units from 0. If y final is, whatever this is, 5.5, looks like it's 5.5 units from 0 on this number line. But dy is the difference between those, or the final value is the initial one plus the change. If I have two changing quantities that are related, that's when we got into more complexity. We had to think about how I take a change in one, multiply it to get a change in the other, and visually speaking, we'd use a two-dimensional graph, not just a number line, but the XY plane is what we've been using. There's other coordinate systems, but if I have two axes, one to represent each of the two related quantities, the value of the independent variable is typically drawn horizontally. That's not always the case, but just kind of a math standard. If nothing is said, we can think, all right, independent variable goes along this way. If it's time or something, that's, you see it across here, whatever it might be though. Our independent quantity, or x, are the general, like, this is the normal for there's nothing really explained, we'll just assume it's that way. But a small change in x multiplied by the constant rate of change m would give me the corresponding small change in y. And why I say small change, when we have a constant rate of change, you can have any size of change you want within the domain, and you'll be okay. But what we're going to be talking about next is things that aren't exactly constant rates of change everywhere. But if you look at a small section of the graph, it will be. So if we have a relatively smooth curve, if you home in on any portion of that, it's going to look fairly straight, like a line. And so we can imagine and use the same exact concept. And that's what's going to get us through to not just talking about constant rate of change all the time. If we look at small sections, most all the functions that we're going to run across are constant rate of change if we look at little pieces of them at a time. And so we can use these same tools throughout the course, not because we're always working with linear functions, but because many, many, many types of functions, all but extremely horrible ones in fact, are some things that you can see have essentially constant rate of change if we look at small sections of them at a time. So in any case, if I make a small change in x, multiply it by this rate of change, this constant rate that relates it to y, and I get the associated change in y. So I could represent this vertical section by dy or by dx, but that's the corresponding amount of change. So if you remember, we talked about a flag problem a little bit ago. We're going to talk more graphically about this on Wednesday, next time I see you. But just before we leave for today, I want to show you two questions really quick. Don't worry about getting the number values, but we had this soldier lowering a flag at a constant rate of 0.75 feet per second. If it started at 110 feet above the ground, and I asked how much has it lowered after 3.72 seconds, not a computation, just what is this asking us to find? A value of y or a value of dy? dy. It's asking us how much this changes. So if I need to find a value of dy, I need this rate and how much x has changed. Oh, well, x has changed by 3.72 seconds. So y has then changed by 0.75 times as much. And y would be measured in meters as opposed to seconds. Or if I ask about b, what is its height after 12.87 seconds? Is that asking about y or about dy? That's asking about y. What is its height? What is its height above the ground? So I need to know its height above the ground. I know where it started. I'm going to append onto that the amount of change. So I have to find a dy and then add it. Well, it's going to be a negative amount of change to the initial. So I find the amount of change during 12.87 seconds and add that negative number onto 110. So just keep in mind when you're answering these sorts of questions, am I looking for a value of a main variable, the x or y variable, or am I looking for an amount of change in that variable, a dy or a dx? All right. Study well this weekend. There are exam topics posted, and there's a Canvas quiz that's posted.
I got one.
It's due tonight, yeah.
But like, it was not